All right, guys, so this is our first practice AP problem of the week. So let's take a quick look at this. This is, obviously, this is an electrochemistry problem. You got the voltmeter, you got the two cathode and anode. We're not sure which is which yet. We'll take a look at it. That's one of the questions. So this says a galvanic cell and the balance equation for the spontaneous cell reaction are shown above. So it gives you the balance equation, which is nice because normally that's something you have to solve for. The two reductions, the half reactions, overall reaction that occurs in a cell are shown on the table below. On the diagram, clearly label the cathode. So, okay, first of all, we have the balanced equation, which is actually very helpful. And here's why it's helpful. What makes this helpful is I take a look and I check to see which side I got Fe with a +3. These are both reductions because that's how they're shown for half reactions when it's given the E reduction value. So that means that if I have MnO4 with a -1 and I see MnO4 here with a -1, that means this one right here is the reduction, which means this is happening at the cathode. So it says clearly label the cathode, so the cathode will be this right here, like that. It has to be. Notice that the Fe +3 is on the other side here, which means that this is actually, this one right here is actually the oxidation part. So this is oxidation because this is written in reverse. So that means that, obviously, if we write it in reverse, if we flip it, that's a reduction. If we flip it back, that's an oxidation. So the cathode is the one with the manganese and the permanganate. So there's other ways you could do it. You could take a look. If you don't want to look at the reductions that are listed here in the half reactions, you can take a look to see that this one goes from a +2 to a +3. Which means that that is oxidation because we're getting more positive. This one goes from a +7. That's manganese for MnO4 is a +7 there. And over here it's a +2, which means that it is reducing in positivity or reducing. So that's reduction. So that's another way you can look at it. Remember, anode oxidation and cathode reduction. So there's a whole bunch of ways you could do this. That's not just one, but that's what I did. I took a look at this to see if this is on the same side as this up here, which means the MnO4 is part of the reduction, which means that that is the cathode. Calculate the value of the standard potential. That means E cell. We know this. We've done this before. E cell equals E reduction of the cathode, right, minus E reduction of the anode. So that basically is saying we're going to do this minus this. So that is 1.49 minus 0.77. Whatever that equals here is going to be our answer. Looks like that's a 0.72 or something like that. That's it, 0.72 for this. 0.72. That's volts. Calculate the value. How many moles of electrons are transferred when 1 mole of, okay, so we're talking about, there's 1 mole is already for us in the balanced equation here. Take a look at down here at the half reaction. The half reactions are given to you, so you might as well use them. Notice that we have 1 mole of electrons transferring for the oxidation, but 5 moles transferring for the reduction. That means I'm going to take this whole thing here and multiply all of it by 5, which is where that 5 comes from and that 5 comes from. We do that so we can get the number of moles on both sides, the oxidation and the reduction, to be the same so we can cross them off for the finished balance equation. So the answer to that is 5 moles of electrons are transferred. Okay, so far so good. We've gotten all the way down to D, and I really haven't had to do much more than just a subtraction problem. So now I'm going to take a look at what we have down here for this D thing. Now I want to keep moving here because I'm running out of time. Calculate the value of the equilibrium constant, KEQ, for the cell reaction 25 degrees Celsius. Explain what the magnitude of K tells you about the extent of the reaction. Great, let's do that. As a matter of fact, if I do that, I'm going to be using a couple of different, okay, all right. I'm going to go over here. It says calculate the value of the equilibrium constant. Here's one thing that we know. We know that this to be true. Oops, that's E cell. Should be that right there. And then I know that this is also true. So the first thing I do is solve for delta G here, and then using delta G, I'm going to solve for the natural log of K by taking my delta G and dividing by a negative RT. Okay, so, and then after this is like that's, I'll do the e to the exponent, and that will find my K then. So let's do the first part. The first part is finding delta G. So what does that mean? What does that mean here? Well, we just did 5 moles, okay? 5 moles of, there we go, 5 moles of electrons transferred. The F, now this is the 96,500, and that's joules per coulomb or whatever it is, and we're going to change that to kilojoules. So automatically I'm going to do 96.5, and that's going to give us our kilojoules per volt, or whatever it is, per coulomb. And then my E is the 0.72, and that's the volts. So kilojoules per volts maybe, so that these cancel here. I'm left in kilojoules, and this is the number of moles. Right there, I get a value. If I multiply those, and just make sure I'm good with this, my value is a negative 347.4 kilojoules for my delta G. So that means when I slide down here, when I try and do the natural log of K equals, that's going to be my negative 347.4, that's kilojoules per mole, or just kilojoules. And then my R is the one that is 0.00. We've done a problem like this already, and we had to change, because this is joules, I changed it to kilojoules to get my kilojoules and kilojoules to cancel. That's why I changed the 8.314 to 0.008314, and then 298 for my Kelvin, like that for the temperature. When I multiply all of this out, what I end up with then is my natural log of K at 140.21, or something very close to that. Now, 140.21 for the natural log of K means to find, I have to put all of this to the E, which means I have to put that to the E. So K actually equals, what I got was something like this. This is an outrageous number. Notice how big this is right there. Times 10 to the 60 literally means 7.8 and then 59 zeros. 59 zeros. Okay, so what that means is that the products are heavily favored. If I put a negative in here, times 10 to the negative 60, that means the reactants are heavily favored. And like that's the difference between the plus and the minus for the exponent. So if you don't believe me, check the work. And what this tells us is that this reaction goes to completion. Okay, that means that the products are heavily favored. All right, I'm going to cut it there so that I don't take up too much of your time.